In this topic, we are going to study Pelton wheel turbine. So, as we have discussed in classification, Pelton wheel turbine is impulse turbine because the total energy available at the inlet of turbine is only kinetic energy. Second, it is tangential flow turbine because the water coming from the nozzle is nothing but tangentially striking the bucket of the runner. Now it is high head turbine because the head is around 150 meters to 200 meters. Okay, so head raise level to the turbine center, the total distance or total head is around 150 meters to 200 meters or even more sometimes. So because of that, these turbines require a small quantity of water. Also, if you see clearly, there is a nozzle connected at the end of penstock. So water coming through the penstock, it will pass through the nozzle. So whatever the remaining amount of pressure energy is there will be converted into kinetic energy before it strikes the bucket of the turbine. It is a low specific speed turbine. The speed is varying from 10 to 35 for single jet turbine. As it is shown in diagram, it is a single jet turbine, so it would be around 10 to 35, and if it is more than that, means double jet is there, then it is around 50. So the specific speed is low. So as you can see, tangential flow turbine, so the runner is there around which nozzle buckets are mounted. We are going to see it in later slide how it is done, or how the buckets are there and how the runner is there. Then there is a needle wall at the end of spear which is in the penstock, and it is covering the nozzle from inside. Again, if you see clearly here, there is a wheel attached at the end of this spear, and at the right hand side of the spear there is a needle. So the needle size or shape is such that it will cover the whole nozzle opening when the wheel is completely rotated towards the right. Depending on the requirement, that is the speed of the runner, the wheel will be rotated clockwise or anti-clockwise. If the wheel rotated clockwise from left direction, it will go inside. If it is rotated anti-clockwise, it will go outside. So when it will go inside, it will minimize the distance or opening, and less amount of water will be striking the bucket. If it is going away, it will open more space for the water to strike the bucket, and the turbine will rotate at higher speed. Then you can see there is a casing. As we have discussed in earlier video, difference between impulse and reaction turbine, the casing of the impulse turbine, that is in this case Pelton wheel turbine, has not any specific hydraulic function to do. It is only to cover this rotating high speed rotating turbine, okay, from any accidents around, and splashing of water is just avoided. Then there is a brake, and also the casing should not run fully by the water. Only this much amount of water is there, and the remaining water will go into the tail race. Then there is a braking jet or nozzle, we can see at the top, which is directed on the back side of the bucket. When the turbine is continuously rotating, when the water is continuously supplied, when the water is stopped from the penstock, if the needle is completely closed, still the turbine will run because of the inertia. So in this case, it is not feasible to rotate the runner, so it should be stopped immediately. May not be immediately, but a slowly stop should be there, which is done by the braking jet or nozzle. So after the nozzle is completely closed from the left side, the water is striking the back of the bucket from the top, from the braking jet or nozzle, which will help to lower the speed of the runner and completely stop it afterwards. This image shows runner of Pelton wind turbine. It is around 30 to 50, 6 to 50 buckets are there. So around 30 buckets you can see. Tip angles, that is 10 degrees to 20 degrees, we are going to see during numericals, and the speed is around 60 to 1000 rpm depending on number of buckets. Okay, this diagram shows the cross section of the bucket. In this case, this is the top view. If you look from the top, you can see the splitter which is in between these two cups or bucket, and this is the splitter. So whatever the jet is coming out of the nozzle, diameter d, it will split into the two jets or two uh, ways as shown. So the splitter provides splitting of the jet. Then there is a notch provided at the bottom of the bucket, and also you can see in the image. Okay, so a notch is provided so that when the rotor is rotating, it will not allow the jet to strike the bucket other than the bucket it is required to get strike. Okay, this image clearly shows a single bucket of the Pelton wheel turbine. You can clearly see at the bottom there is a notch, then there are two halves of the bucket, there is a splitter in between the two buckets. So when the jet strike, it will strike exactly at the center of the splitter, and the jet will get split into two. Then at this end there will be holes and arrangement for attaching the bucket to the nozzle, to the tunnel, sorry.